Okay, so this is the first of two class meetings that are taking place while I'm away in Amsterdam at the SIAM conference on computational science and engineering. So I'm just pre-recording uh, these and going through my notes. Okay, so um, the topic that I'll be covering this time, actually, I need to change this a little bit. Section 4.5.1 and 4.5.2. Where I'll be looking at some different least squares problems. So far, we've seen the full rank least squares problem, also rank deficient least squares. Now we're going to look at least squares with some kind of constraint. The idea is to minimize the norm of b minus ax as usual, except x has to satisfy some kind of constraint. First, we'll look at linear constraints on x, and then a quadratic constraint. Okay. So one application in which least squares with linear constraints comes up is like you're trying to fit data, like in a least squares problem, for example, like finding a line or higher degree polynomial as an example that fits some given data. But you might not get a good fit if you try to use just one kind of function on the entire domain of a data. For example, if your data is some function of x, maybe the function has a very different behavior on different parts of a domain. So it's not uncommon to use different functions on different subintervals. One extremely common application of this is cubic splines, piecewise polynomial. You use different polynomials in different subintervals, and you chain them together in a way that's smooth. So cubic splines is what I'm referring to there. Okay. Um, so, and as I said, you want it to be continuous. If you'd like to have its derivatives continuous too. So that leads to constraints on the functions that you're using to fit the data. All right. So that's just one example of the abstract problem of a least squares problem with linear constraints. So now I'm going to give you the um, general form of a least squares with linear constraint problem, and I'll show you two different approaches to solving it. So as before, we want to find x that minimizes b minus ax for a two norm for some given a and b. And here's our constraint. We require that the solution x satisfy this equation exactly. So we have some given matrix C and some given vector D that prescribe linear constraints. And since this is a linear operation, that's why we call it linear constraints. So A is a M by N matrix, as before. X is an Rn, and the number of constraints is given by P. So here we have a system of P equations, but in the N unknowns, X. So one approach to solving this that you may have seen in your multivariable calculus class, if I presented it a different way, is a method of Lagrange multipliers. So the idea is to solve this constrained minimization problem by solving an equivalent unconstrained minimization problem. So instead of simply trying to minimize this, we try to find a minimum of this function right here. So we add on this term. The vector lambda, that's the vector of Lagrange multipliers. So why does this work? So what you do here is if you take the gradient of f, first with respect to the x variables, and then also with respect to the lambda variables. So so what happens here is these two combined make up the entire gradient. So to find a minimum of this function, you want the entire gradient to be the zero vector. So this has to be zero, which leads to the constraints being satisfied. Here, this part is the gradient we would get from the unconstrained least squares problem But because of the constraints, we have this extra term added here. Now, to solve this to solve a system at the requiring the gradient to be 0. So in other words, setting both of these equal to 0 is equivalent to this system of equations here, because here we have A transpose X plus C lambda is equal to A transpose B. That's from a gradient of f with respect to the x variables. And then here we have C transpose X is equal to D. That's from a gradient with respect to the lambda variables. Okay. Now, so what we do is when we write out the system of equations, this is what we get from the first block after some rearranging. So basically, it's like we're solving the normal equations, but with an extra term added on the right-hand side. So if we go ahead and write out the formula for x from here, keeping in mind that we don't know what lambda is yet, but we have this expression for x anyway, notice that this first term here, that is a solution to the least squares problem with no constraints. Now, that's just a solution generated by the normal equations. So this part here referred to as x hat. So we can think of the solution to our constraint problem as a solution to the unconstrained problem plus this extra term. All right. So what remains is to find this. So to get an expression for this term, lambda here is still unknown. What we could do is multiply both sides by C transpose. But we know that this is equal to D. So now everything in this equation is known except for lambda, but we now have a system of equations that we can solve for lambda. So now the things we certainly don't want to form this matrix explicitly because we have this inverse here in the middle of it. But if we break it down to stages, we can have a practical algorithm for solving this system and then getting our solution x. So here's what we can do. First, we get x hat. We already know how to do that, though. We take the QR factorization, but the economy size or thin QR factorization will be enough for our purposes. And this is ground I've covered before, that we can take the R from the thin QR factorization and solve a system involving R. So this is upper triangular. So we're solving this by back substitution to get the regular or unconstrained least squares solution, our x hat. Now, A transpose A is the same as R transpose R, and you would see that if you replace A with QR in here and work out what it is, because you get a Q transpose Q in the middle, which is identity. So then I'll replace A transpose A with R transpose R in here. So that's a step towards simplifying this, but we still don't want to form this matrix explicitly. If we keep in mind that R transpose R inverse has this form, just using the properties of the inverse, inverse of a product is a product of the inverses in reverse order, then I have, so this system is equivalent to this one, where the matrix W is defined to be R inverse transpose C. So if I can get W efficiently, then this is no problem to solve. So again, you don't want to compute this inverse explicitly. Instead, what you do is you solve this system of equations. R is upper triangular, so its transpose is lower triangular. So we would solve this system for one column of W at a time, and you get each column using forward substitution. So that'll be an efficient process. Now, to solve this system, once we have W, and we still don't want to solve it this way, we don't want to form W transpose W explicitly because there's loss of information due to rounding error when you do that. But that's okay. What you can do is QR factorize W. So again, it's an economy size or thin QR factorization. And we have this system as a result that's equivalent to this one. Just as A transpose A is equal to R transpose R, W transpose W is equal to U transpose U, where U is the upper triangular part. Okay. So we just solve these two systems using first forward substitution for this one, back substitution for this one. So now there's a lot going on here, but it's all I'll present to you the overall algorithm in a moment. So this is our original formula for X, but A transpose A is written in terms of R transpose R to get us this. But this right here is equal to W times lambda, and that comes from the various formulas that have been worked out here. But R inverse transpose C, that was seen earlier. That's a definition of W. So we can fill that in here. Okay. Now, we don't want to compute this explicitly. Instead, we label this vector Z. So then RZ equals W lambda. So whenever you see an expression involving a matrix inverse, you don't compute it explicitly. You think of it in terms of solving a system. Just as you want, just as the solution of AX equals B is X equals A inverse B, assuming A is invertible, you use that kind of relationship here too. So putting everything together that I've just shown you, this is the overall process. So to QR factorize A, this is just from standard QR approach to solving the unconstrained least squares problem, which gives you X hat. Then we've obtained a matrix W by solving this system by column by column forward substitution. QR factorize W. And then the upper triangular matrix U we use down here to solve this system by forward substitution, and then this system by back substitution. So these two systems together give us the vector lambda, the Lagrange multipliers. Then we solve for our vector Z by back substitution, because our R is upper triangular. And then we subtract Z off from our unconstrained solution to get our constrained solution. And that's the whole algorithm. Now, there's one problem with this algorithm, and that is we were originally trying to find, our goal is to find X, which has n variables, and P constraints are applied to them. But then we recast a minimization problem of constraints as one of solving the problem of minimizing F that depends on both X and lambda. So now, instead of trying to minimize a function of n variables subject to P constraints, we're trying to minimize the function of n plus P variables with no constraints. The thing is, when you impose constraints, that takes away degrees of freedom. So you would think that it takes away degrees of freedom in your solution. So you would think that the presence of the constraints would lead us to solve a system involving fewer unknowns, not more unknowns. So it's worthwhile to consider a different approach where we solve a smaller system, not a larger one. So For an alternative approach, instead of QR factorizing A, we'll actually QR factorize C. Okay, so C is an N by P matrix, and we're assuming here that N is greater than or equal to P. And also that C has full column rank. And that's important because otherwise we could be putting ourselves in a situation where, because maybe the constraints can't be satisfied, the constraints had to be exactly satisfied. Okay, so this is the full QR factorization of C, unlike the thin QR factorization of A we were doing earlier. So keep in mind when what follows, Q and R refer to C, not A. So now we rephrase the constraints as in terms of these two systems. So if you replace C with QR, and then break this down into two stages, so X, so we define U to be Q1 transpose X, but U has to satisfy this system. All right. Now, for convenience, we're going to define the other portion of X, Q2 transpose X, and call that V. Now, I want to minimize B minus AX. So, forgot all my subscripts here. This should be, all of these norms are two norms. Okay. All right. So then just writing out, so I put a Q in here, and then replace Q by its block decomposition. Okay. And then now I have this that I want to minimize. And for convenience, I defined A2 to be AQ2. So right. Okay. Now, the thing is, once I QR factorize C, I go ahead and solve this system by forward substitution, because R1 is upper triangular, and that'll give me U. So this is effectively one portion of X. Now, at this point, so in other words, by the time I get here, the vector U is known. Everything in here is known except for V. So here's an algorithm, an alternative algorithm. So I go ahead and QR factorize C, solve for U, and then if I define this vector Z here to be Q1U, and then I also define A2 the way I did earlier, then, all right, so this vector Q1U here, that's Z. So now I have this that I want to minimize, but this part is known. It's only V that's unknown. So this is an ordinary unconstrained least squares problem for V. So I can now go ahead and solve this by whatever means, normal equations or QR factorization of A2. I could do that, and then I get so the solution I get is V. Now keep in mind how V was introduced. V is equal to Q transpose X. So if I multiply both sides of this equation by Q2, now Q2 transpose Q2 is identity. The other way, Q2 transpose is not identity, but it is a projection of x into the range of Q2. So z right here is a portion of x that belongs to the range of Q1. This vector right here is a portion of x that's in the range of Q2. So all I have to do is take my vector v, multiply by Q2, and I have that portion, and then I'm done. So what happens in this case is, if we look at the size of a problem is each step of the way, here I'm solving a system of equations involving p unknowns. So that's a smaller system than what we had before of Lagrange multipliers. And then our decomposition here, Q1 is C is n by p. Q1 is also n by p. Excuse me. So Q2 has n rows, and it has n minus p columns. So the vector here that we're solving for, v, has only n minus p elements. So here we're solving for a vector with p elements and then n minus p here. So sure enough, we're solving our original problem where we have n unknowns, solving for x, and breaking it down into two problems, each of them having fewer unknowns. And that's what we would expect when you're solving a constrained problem, that it reduces the size of a problem. Okay. So another nice thing about this algorithm, besides the fact that we're solving systems with fewer unknowns, is that this system is possibly is at least as well conditioned as the original least squares problem involving A, but it could be better conditioned. Now, on the other hand, so if the system is if the original least squares problem involving A and C, if A and C are sparse, that sparsity can be destroyed. So that's one unfortunate aspect of this. Okay. So this MATLAB function, LSQLin, can be used. There's many different ways to call it depending on the kind of problem you're trying to solve, but it is a function that can be used to solve a least squares problem with linear constraints. Now, here we only considered equality constraints. C transpose X must equal D. You can also have constraints of this form where you have some matrix C times X, and all the elements of this vector must be less than or equal to the elements of this given vector. You can also impose upper and lower bounds on the elements of X. Okay. Now, before I get into least squares of quadratic constraints, one aside from the least squares of linear constraints problem is a problem solving an underdetermined system. So we talked about overdetermined systems before. That's from the beginning of this least squares discussion. Now, as a recap, if we have this least squares problem, where we have more rows and columns, and A is full column rank, then we know that this is the solution. That just comes from the normal equations. So that's overdetermined. If we have fewer rows and columns, but we'll assume that A has rank n, so at least has full row rank, then what happens in that case is, because it has full row rank, whatever vector B you have will definitely be in the range of A. So this is a situation where A equals B has infinitely many solutions. As I mentioned before, because it's not unique, we can ensure uniqueness by imposing some additional condition on X, for example, requiring that it have minimum 2 norm. Now, we do know how to get the minimum norm solution from the last class using the pseudo-inverse, but I want to come up with a formula that's somewhat similar in appearance to this one. So what we could do is we can cast this as a least squares of linear constraints problem. So the goal is to minimize the 2 norm of x subject to these constraints. Ax must equal to b. So we think of the general least squares of linear constraints problem that was described. Okay, it's not good formatting there. All right, so in general, for least squares of linear constraints, we want to minimize b minus ax and satisfy C transpose x is equal to D. But here, we just want to minimize the 2 norm of x in our problem. So B would be 0, A would be minus identity, and then C transpose would be the A from our underdetermined system. And then D would be equal to B. So by assigning everything here to the right quantity, what we have is a least squares of linear constraints problem. So I'll scroll back to there. Yeah, so these are the substitutions that I have in mind. Now, here's the formula for the solution of a general least squares of linear constraints problem. For generic, minimizing b minus ax and with c transpose x equaling d. So if I make these substitutions here, so b would be 0, where we see a here, that'd be minus identity, and so forth, then the solution for the unconstrained problem in this case is just going to be 0. So now what we have to do to get the vector lambda is solve this system involving A transpose instead of a customary A transpose A. Once we have lambda, we can multiply it by this. And this is our formula for the minimum norm solution of the underdetermined system of linear equations Ax equals b. So notice it's quite similar in appearance to the formula for the least squares solution in the overdetermined case, which is unique if A has full column rank. So there's a certain symmetry to it. But here we have A transpose instead of A transpose A. Also, here the inverse is a second matrix in the formula, whereas here it's a first matrix. All right. Lastly, I'll show how to solve least squares problem with quadratic constraints. So we still want to minimize the norm of b minus ax, but now we require that the 2 norm of x is equal to some value, alpha. And here alpha is less than or equal to the 2 norm of a minimum norm solution. So a pseudo inverse of A times B. One of the homework problems from a section is to consider, what would happen if you had to solve this problem where alpha is strictly greater than this 2 norm. So how you would handle that situation is very different. But this is where you take into account the fact that that this is the minimum norm solution, and you want some solution X that has a particular norm that's greater than that. So something needs to be added on to it. Okay. This kind of problem comes up if A is particularly badly conditioned or ill-conditioned. Because you go ahead and try to solve Ax equals B by conventional means, but because of ill conditioning, you might have a solution of wild oscillations, noise, and imposing a constraint on the 2 norm of a solution is one way of regularizing it to get rid of such artifacts. A particularly well-known example of that is called Tikhonov regularization. All right, so once again, you can use Lagrange multipliers. So it's And Lagrange multipliers is for any kind of constraint, linear or nonlinear. So we have this we need to be minimized, and we need this term to be 0. And we have just a single Lagrange multiplier that's mu. So, um, so what's done here is to actually I should indicate that this is the gradient, not the entire gradient, but with respect to the x variables. The gradient of this with respect to the to mu is just this, which we want to be 0. Okay, so require this to be 0, but we also require the rest of the gradient, this portion, to be 0, and that's equivalent to solving this system here, where we have A transpose. So it's like the normal equations, except that the matrix A transpose A is shifted by this unknown value mu. One of the homework problems is to show that uh, this matrix here is at least as well conditioned than A transpose A. So in other words, the condition number of this is um, less than or equal to that of A transpose A. The problem is we don't know mu. Now, from the general solution formula for X, just by inverting this matrix, and if we take X transpose X using this expression, we get this down here, and this has to be equal to alpha squared by the quadratic constraint. Now, suppose we compute the singular value decomposition of A. So A is equal to U sigma V transpose, from last class. Then all I've done here is I've replaced A throughout with the singular value decomposition. So this is just this right here. But now there's some simplification. Okay, where all of the V's end up canceling out. And then if I define, here we have U transpose B. If I label that vector C, that simplifies things a little bit, because if I have the SVD, then this is known. Now, so what I can do is, in terms of the components of a vector C, I can express this using this summation, where the sigma I are the singular values of A, the Ci are the components of C, and then we have this unknown value mu here. And what I'm going to do is I'm going to call this function chi of mu. So chi of mu, for whatever value mu I'm looking for, must be equal to alpha squared. Now, this function is undefined, of course, when the denominator is 0. But that only happens when mu is equal to minus sigma I squared. But if we go back to, but that means that this function is at least well defined for non-negative mu. All right. And I should mention that this assumption on mu was defined at the beginning, and if this matrix being better conditioned than A transpose A can only hold if mu is non-negative. Also, as mu goes to infinity, then the denominator would overwhelm the numerator, and chi would go to 0. Okay. So what we have here is a nonlinear equation satisfied by mu. Setting this equal to alpha squared. So this leads to this algorithm for solving least squares of quadratic constraints. So I go ahead and compute the singular value decomposition of A. I compute the vector C using the U from that decomposition. And then what I do is I actually solve not chi of mu equal alpha squared, but 1 over chi of mu is equal to 1 over alpha squared on this domain using Newton's method. So that's a well-known method for solving a single nonlinear equation. So you choose some initial guess somewhere in this domain and apply Newton's method. It repeatedly computes the, in this case, mu intercept of a tangent line approximation to this function. Once we have mu, then we can substitute it into this formula for x. Well, this formula is simplified, taking into account that we already have the SVD of A. So we have the equivalent formula here. Now, it seems strange. It might seem strange to solve 1 over chi equals 1 over alpha squared. Reason for that is, as I mentioned, as mu goes to infinity, chi goes to 0. Its derivative also goes to 0. Functions of small derivatives that are nearly 0 in absolute value cause problems for root finding methods such as Newton's method. So if we choose a function with a function that is steeper, then Newton's method will perform better. Oh, that's actually the end of the notes. Okay, so as far as the homework problems from this section, there were 3 that I assigned. Okay, one of them is a coding problem where you're just coding one of the algorithms, and that using MATLAB's QR function, it translates in and backslash. That algorithm translates in a fairly straightforward manner, so there's not too much to that one. That's talking about problem exploration 4.5.1. The next one is 4.5.4, showing that A transpose A plus mu identity has condition number less than or equal to that of A transpose A. I suggest using a singular value decomposition for that one because that gives you a way to express, because the condition number, of course, is norm in a 2 norm of a problem states. So you're looking at working with the 2 norm of A times the 2 norm, sorry, not 2 norm of A, 2 norm of the matrix A transpose A plus mu I times the norm of its inverse, as opposed to the 2 norm of A transpose A times its inverse. You have the simpler formula for the condition number in a 2 norm. It's the smallest, the condition number to 2 norm is the matrix's largest singular value divided by its smallest. So using that simpler formula for condition number, you can show that A transpose A plus mu I has the condition number is no larger anyway. The last problem that I assigned in the section exploration 4.5.6 that I discussed earlier. Okay, so it's a situation, what if alpha is strictly greater than the 2 norm of the minimum norm solution? So you wouldn't have to go through everything that I've described here. There'd be no need for that. So in that case, the solution of the least squares problem of quadratic constraints can be expressed as x equal to this plus something. And the idea is to figure out what is that something. Okay, so that's that. And then I will pre-record one more class, and that'll be getting into certain iterative methods for solving AX equals B. And if you have any questions about anything I've gone over in these notes, by all means, let me know.